Hello, welcome to Einstein's Mechanics once again. Today we are looking at the application of differentiation and what aspects are we going to look at? We are looking at rate of what? Change. So to apply differentiation in our daily activity, let's look at how rate of change is going to be useful when we apply differentiation. When we talk about rate of change, we mean how one variable is changing with respect to what? The other, to the other variable. Let's say x. Are we good? So now we have a variable y and x. So the rate of change of y with respect to x is written as dy on what? Dx. Meaning as x changes, the rate at which y will what? Change. Y now becomes what? The dependent variable because it is dependent on what? X, and x becomes the independent what? Variable. Are we good? So if we are saying y changes with respect to t, then we are going to write it as dy on what? The t. If y changes with respect to theta, we are going to say dy with respect to what? Theta. Are we good? Always the question or the problem is going to tell you what the dependent variable is changing with respect to. But rate of change, anytime a variable is changing just with the rate, meaning we are considering what? Time. Rate means what? Time. We are referring to what? Time. So, in a particular question throughout our solution, if we see that y is what? Changing without with respect to nothing, the question is not giving us any other parameter at which it is changing, but at a rate, meaning y will be changing the y with respect to what? The t. Pay attention to that. If we want y to change with respect to any variable, we will say y is changing with respect to, let's say, x with temperature, with pressure, then to be dy over that. But if it is changing at a rate, meaning dy on what? The t. If x is changing at a rate, then our derivative will be dx on what? The t. Are we good? So these are the applications of what? Differentiations that we are going to use. It's very interesting and it is used in solving many questions. So for example, if I want to see the rate at which my electric current is what? Changing. The rate at which, so let's say rate at which current is changing. So I'll represent my current with what? I. And since it's a rate with respect to what? Time. So that will be di on what? The t. The rate at which current is changing with respect to time. And this is what? Rate of current change. Are we good? And we are good to go. So let's look at some examples that we've got that we will solve with this approach. The length L meters of a certain metal. So the length, one parameter is given as the length in meters of a certain metal at a temperature. This degree Celsius is given by, so this is the length of a certain metal rod. It is given by this formula. Determine the rate of change of length with temperature. Do you see that? The rate of change of length, the length is changing with what? Temperature. But if it was determine the rate of change of length, that would be length changing with what? Time. But here it was specific with temperature, when the temperature is that. So let's look at how we will do it. So we first, from the question, I have my length formula L, which is 0.5 theta, which represent the temperature, plus 4 theta squared. Are we good? So this is it, that we have our length. Then can we are determining the rate of change of length with temperature. So this length is going to change with temperature. And truly, the equation of the length involves what? Temperature. Remember, it says theta degree represent what? The temperature. So can we say the length is changing with temperature? Are we good? So we can say let L equal to what? Length, and this T equal to what? Temperature. As temperature. So the rate at which the length is changing with respect to temperature, we have to differentiate this equation, and we know how to differentiate it. Very simple. So this will be 0.0 plus with respect to theta. So that will mean 2 will multiply this whole thing, giving us 8. Still another theta. So this is the rate at which the length is changing, the equation at which it is changing. So the question says determine the rate of length with temperature when the temperature is 100 degrees Celsius. So meaning anytime I put the temperature value here, I will get the rate at which the length is changing. So first, at the 100 degrees Celsius, the L on the T is going to change this way. Then theta, which is 100. And if you punch this one, you are going to remember the L is in meters, so the equation is already in what? In meters. And when you punch this one, your DL on the T is going to give you 0.00013. Use your calculator. Meters. It was in meters, and the temperature is also in degrees Celsius. So since they are divided per degree Celsius, if you want to convert it to millimeters, then our DL on the T is going to give me 0.13 millimeters per change in what? Temperature. Are we good? So B at 400 degrees Celsius. So B at 400. So DL on the T, which is equal to, you just put in 400 at the theta, which is 400. Meaning at 400 degrees Celsius, the temperature or the length is changing at this rate, meter per degree Celsius, which can be sent to millimeter as 0.37 millimeter per a change in what? Degree. So this is the solution. Are we good? This is the solution for the rate of change. Let's look at the next problem. The radius of a cycle or a circle is increasing at the rate of 0.01 centimeter per second. Find the rate at which the area is increasing when the radius is what? 5. So let's write down the parameters. So solution, things we have here, the radius is changing. So let R be what? Radius. And let our A be area, and the radius is what? Increasing at the rate of 0.01. Is it increasing with any other parameter? No. At the rate of what? No other parameter. So meaning changing with time. Even if you look at the unit, centimeter per what? Second. Meaning radius per time. So can we say our dr on what? Dt is equal to 0.01. Check the unit, it will give you the clue. R per second, which is time. Are we good? Find the rate at which the area is increasing when the radius is what? 5. Area is increasing. Can we know the area of what? A circle? Yes. The area A of a circle is what? Pi r squared. Given that the radius is what? 5. And our r is equal to 5. centimeters. Most of the problems like this, we use the chain rule. The chain rule. We remember the chain rule? Yes. Let's say the chain rule dy on dx, which is equal to dy with respect to the t and the t with respect to what? Dx. This way, this is what we call the chain rule. So we are trying to establish, because we are having two parameters, radius relating to area, we have to express them in such a way that the chain rule will be what? Obeyed. Are we good? So first we have our dr on our dt. We have the area. Can I differentiate the area with respect to the radius? Yes. Look at dA with respect to dr will be equal to, I'm differentiating this with respect to r. So can I say I'm getting 2 pi r for dA on what? Dr. And the question is saying find the rate at which the area is increasing with what? Just increasing. So meaning find the rate at which the area is increasing. There's no other parameter added, meaning we are going to increase with what? Time. I hope you get it. So what if the question has said find the rate at which the area is increasing, maybe with temperature, with other thing? That means we would differentiate with respect to that parameter. But here, at which the area is increasing with time. Are we good? So what are we finding? We are going to find the A with respect to the T, which is unknown. And can I make an analysis from the chain rule and get the equation the A on the T? Can I say the A on the T will be equal to, yes, the A on the R multiplying the R on the T? Are we good? So they look similar. This is a perfect chain rule what? Established. Therefore, my dA, the rate at which the area is increasing with time, dA on dr is here, which is 2 pi r multiplying the r on the t, which is 0.01, and that is what we are what? Getting. But looking at this, I have the value of what? R, which is dA on the t, which is 0.01 multiplying 2 pi, and my r is what? Giving us 5. So can I bring 5? And when you punch this variable, the area is increasing with time at 0.1 pi centimeter square per second. Remember, it's area, so centimeter square per second. And this is the final solution at which the area is increasing. I've taken my time to explain your rates. Let's look at the third example. The radius of a balloon is increasing. The radius of a balloon is increasing at a rate of this. Are we good? So, meaning with time, even if you check the unit centimeter per second. So, radius, that means the R on what? The T is increasing at 10 centimeter per second. From the beginning, you can say let R be radius, okay, T be time. So we have our dr on the T. At what rate is the surface area increasing when the radius is what? 15 centimeters. So we have area to mention. So A be what? The area. And the surface area. The surface area of a balloon assumes what? To be a sphere. So the surface area will be what? For that of a sphere. And what's the formula for the surface area of a sphere? Which is A. Let's use surface area S for sphere. And that will be 4 pi r squared. Are we good? All right. So now I have my dr on the T, and the question is asking for the rate at which the surface area is increasing, meaning with also time. So the S, the surface area increasing with time, will be unknown. But from this, can I also get my ds with respect to r? Remember, pi is a constant. It's not changing. changing here is what? The R. Are we good? So can we say the S on the R is equal to 8 pi R for that? Therefore, if I'm looking for this, I can establish the chain rule from these 2 points. So my dx on my dt, are we good, is equal to my ds on the r multiplying my dr on my dt, and this is the chain rule. So the s on the t is equal to, what is the s on the r? Which is 8 pi r multiplying the r on the t, which is 10 centimeters. 10. Are we good? But the question gave us that r is 15, where r is 15 centimeters. So I can put it in and say the s on the t is equal to 8 by this 10 multiplying pi on 15. And when you punch this one well, you are likely to get the s, the t to be equal to 1200 pi centimeter square per second. You can convert it to decimals, but I prefer leaving it this way. Since x is surface area increasing with respect to time, you're going to get centimeter square per second, and that's interesting. So you see, your chain rule should always be established. Example 4. A cylindrical tank of radius r, which is what? 10 centimeters. So let's use the radius, which is r, is equal to 10 centimeters. Is being filled with wheat at the rate of 314 centimeter cube per second. So from the question, you can see what rate this is. Centimeter cube means what? Volume. Are we good? And per second means with respect to time. Good. So my dV, which is volume, with respect to dt, is going to be 314 centimeter cube per second. How fast is the depth of the wheat increasing? How fast is the depth of the wheat increasing? Depth means what? Height. Height increasing. So that one will also be increasing with what? No other parameter means with time. So we are looking for the h with respect to the t is what? Unknown. But first we have to get an equation of the volume of a cylindrical tank. Are we good? Since it is changing, let's look at this way. We have this cylindrical tank. This is it. This is the tank, and this is the height, h, and this is the radius, r. Are we good? And this is filled with what? Wheat. It is filled with wheat, and at the rate of 314 centimeter cube per second. We want how fast the depth of the wheat is what? Increasing as we continue filling. How fast is it increasing? Are we good? How fast is it increasing? That's what we want. And the radius is giving us what? 10 centimeters. But we know that for a cylindrical tank, the volume V is giving us pi r square what? H. Pi r square h. So since I have pi r square h and I'm looking for the h on the t, can I say, look here carefully, you can differentiate the v with respect to r, but is that what the question is asking? No. How fast the depth, height is increasing. So we have to find the v with respect to the h. Differentiate with respect to h. That is going to give us pi r square, because this is just h. If you differentiate, it will be pi r square. And I'm looking for that. So if I want to establish the chain rule from this equation, what would I do? Are we good? So can we say that we are looking for this? So if I'm to make the H the subject, the H on the T, then the formula should be the H on the T multiplying, let's say we want to establish the H on, but we have the V on the H. Are we good? We have to get that. The V with respect to the T is the same as the V with respect to the H multiplying the H with respect to the T. Is that good? Yes. From this three and that and that, I can have this good chain rule. But the question is demanding for the H on what? The T. Is that right? Yes. So can I put in the values? Do I have the V on the T, which is 314 centimeter cube per second is equal to, do I have the V on the H? Yes, which is pi r square. And I'm looking for the H on what? The T. I already have my R. So can I say the H on the T is the same as 314 on pi r square, where my dh on the t is going to be 314 on pi r. R is what? Is giving us 10, and the 10 is square. And from this, if you make it the subject, your final answer is supposed to be 0.999 h, which is centimeter time per second. So you can run it to the h, the t will be 1 centimeter per second. So the rate at which the depth is increasing is 1 centimeter per what? Second. And we are good to go. Let's look at our last example. So a cylindrical ice block, pay attention, another cylindrical ice block of base radius r is melting in such a way that the total surface area, A centimeter square, is decreasing at a constant rate of 72 meters square per second. Given that the height is twice the radius, calculate the rate of change of r when r is equal to 5 centimeters. This question is quite interesting and involves a lot. So since it is a cylindrical ice block, can I make the sketch? And I have it here. So this is the cylinder. I still have my r radius. Are we good? And I still have my height here, h. So this is it. Are we good? And let's write down our parameters. Is of base radius r is melting in such a way that the total surface area A, we have total surface what? Area A. For a closed cylinder like this, what is the total surface area? So we can say let A be the surface what? Area. And what is the total surface area for a cylinder? The surface, we have one circle, the bottom and the cross section. Are we good? So if we combine, we are going to get our 2 pi r square, which represent the two circles, plus our 2 pi r on each, the other side, the cylindrical part. So this is the total surface area for the cylinder. Are we good? And we have it. And it is decreasing at a rate of 72 centimeters square. The area is decreasing at a rate, that means with respect to time, and it is decreasing. Pay attention. All what we've been doing was increasing, but here it is decreasing. So can I say the area decreasing with respect to time is equal to negative 72 centimeters square per second. Why negative? Because it is decreasing. If it is increasing, just positive 72, but since it is decreasing, negative 72. Are we good? Given that the height is twice the radius, height, and we also have the height h is equal to twice the radius. We have this established. Calculate the rate of change of r when r is what? 5 centimeters. So we are to find the r, the rate of change, meaning with respect to time is what? Unknown. And our r is given as 5 centimeters. So these are our parameters. We have to establish a good chain rule. So first I have one and I'm looking for this. I have to get the third one. Are we good? I have to get the third one so that I can make use of what? The entire equation. The entire equation. But look at this way. This is in terms of r. This is in terms of what? T. This was also in terms of t. So we have to get another a with respect to what? R, such that the equation will be what? Valid. Are we good? So from the surface area, we have A to be 2 pi r squared plus 2 pi r h. We are going to differentiate with respect to r because the question is asking us to calculate the change of what? R. But we have a certain h here. And the question is saying for each h, it is twice the radius. So I can say my a should be 2 pi r squared plus 2 pi r on 2r. And when you combine this, you're going to get a 2 pi r squared plus another 4 pi r squared. Since they are like terms, you are likely to get 2 of pi r squared and 4 of what? Pi r squared, which is going to give you 6 pi r squared. Therefore, my dA with respect to what? R is going to give me, you are differentiating this with respect to R, and that will be 12 pi R for that. So now we are looking for the R, the T. Can we establish our equation? Yes. So my dr on the T, the proper equation is supposed to be dr on the A multiplying the A on the T. But you ask, do we have the A, the T? Yes, negative 72. Do we have the R, the A? No, we only have the A, the R. But don't be confused. The A, the R is the same as 1 over the R, the A. So just the inverse. You see, this is just an inverse. Are we good? So if you inverse this, you are going to get the A on what? The R. Therefore, this the R on the A, which will make the chain rule a better rule, is the inverse of whatever is here. Is that right? Okay, so can we say that the R dt will be equal to, since this is the R dA and I have the A dr, inverse 1 over 12 pi R multiplying this, which is negative 72. Don't forget your negative. So my dr on the T is going to give me 1 on 12 pi multiplying this R, which is 5, multiplying negative 72. And when you solve this, you are going to get your dr on the T to be 6 on 5 pi centimeter per second. So the rate at which the radius is increasing or changing with respect to, don't forget your negative. So this will be negative. So the radius will be changing at this negative 6 on 5 pi centimeter per second. And I hope this helped you a lot. Thank you for watching this episode. Let's check the next episode for another application of differentiation.